Should we? Okay, good morning. We're more than halfway through. Exciting. Today I wanted to talk about the relations with topological field theory, which is particularly exciting to speak about here, since a lot of the math that goes into what I'll say was, I believe, developed in this university. So I want to relate geometric Langlands program to the topic of topological field theory. Let me first review what do we have so far. So I'd like to review first the formal structure that we've seen emerging of the geometric Langlands program. And I'm going to change some of my notations as I do this. So what's our first? So we aren't yet talking about topological field theory. We're just reviewing geometric Langlands. So to the first bit of structure, if X is a Riemann surface, we assigned to X a Riemann surface, compact Riemann surface, we assigned some kind of object, which is a differential graded category, and which I'm going to give a slightly funny notation. I'm going to call it ZG0 of X. And this is just a new notation for the derived category of D modules on bungee of X. So this is the object we've been studying so far. We look at the derived category of D modules on bungee of X. And what structure do we know about this is we know that if you're given X and X, this carries an action. This category carries an action of Hecke operators. So this category has symmetries for every point in X of corresponding Hecke operators. So this ZG0 of X carries an action out of the Hecke operators. And now what are the Hecke operators? Well, we introduced Hecke operators as we looked at the loop group, and we looked at its quotient by the positive loops. This is the affine Grassmannian. And then we looked at kind of functions on the affine Grassmannian that are invariant under LG+. So we think of these some kind of LG+ bi-invariant function theory of the affine Grassmannian. So in fact, yesterday we didn't put the derived. We just looked at the abelian category of D modules. But we described the abelian category as representations of the Langlands dual group. And the derived category I'll denote by something I'll call rep dg of g check. So this is some version of the derived category of representations of G dual. It's slightly more subtle. But on the level of abelian categories, we know that D modules on the Grassmannian, which are LG+ invariant, were given by representations of the dual group. In fact, this was our definition of the dual group. So this was the Hecke operators. So I'd like to have a slight reformulation of this. So how do we reformulate this? So I'm going to look at the Riemann surface P1 and try to draw it, something like this. And now if we look at, we try to look at the space of G bundles on P1. G bundles on P1 have a very nice simple description. If I give you a G bundle on P1, I can trivialize it on the top hemisphere. I can trivialize it on the bottom hemisphere. And I get a transition function on the circle. And so this gives me a description of G bundles on P1 as the loop group. So this is a map from this circle to the group G. And then I need to mod out by changes of trivialization on one hemisphere. So these are maps that extend into the interior of the disk. And I need to mod out by changes of trivialization on the other hemisphere. So, well, this is a group in this picture, it's a group that's isomorphic to to LG plus, but it's sort of a different subgroup. It's loops that extend the other way. So we have kind of positive Fourier series and negative Fourier series in G. So what we notice is that this Hecke space, this quotient of the affine Grassmannian by LG plus, looks very similar to the space of G bundles on P1. And in fact, combinatorially, it's equivalent. So the set of orbits here and the set of orbits here are in bijection. They're both given by these irreducible characters of the dual group. So I'm going to pull a little trick, and I'm going to switch from this category to something. I'm going to replace the Hecke category. I'm going to replace the Hecke category by ZG0 of P1, which means look at LG mod LG plus mod LG minus D. So this category is not exactly equal to this category, but they're essentially the same. One is a completion of the other. So up to some issue of finiteness, here all the orbits were finite dimensional. Here all the orbits were finite codimensional, but the categorical structure is the same. So I'm going to blur this distinction and say that what we really have is we have the following picture. We have a Riemann surface we assign to it a category, and for every point in the Riemann surface, we have an action of the category of associated to P1. Okay. So this is a reformulation of the structure we had so far. Does this seem reasonable?
Is this derived variant, is it formally the same as some equivariant?
Yeah, that's for me the definition of this. It's an equivariant derived category of the affine Grassmannian, except that now it's equivariant for LG minus instead of LG plus. Okay, so I'm going to blur the distinction here, and they're essentially the same thing up to some issues of completion. And okay, so this is one story we had. Now, what was the other side of Langlands reality? We had another story, which is to X a Riemann surface. Well, I could say the same Riemann surface. To a Riemann surface, we also assigned another category, which I'm going to another DG category, which I'm also going to call Z. But now, let me use the notation Z G check. So this is something associated to Langlands dual group, and I'll put the infinity here rather than 0 to distinguish from the other notation. So the other category we had was the derived category of coherent sheaves on the moduli space of flat G-dual connections. So this is the other object we had. The geometric Langlands correspondence was an equivalence was a conjectural equivalence roughly between this category and this category. But it had more structure. It also had symmetries. So in this category, it also has symmetries. Okay. So what are the symmetries here? For X and X, we got an action. Of representations of the dual group on this category by tensor product. They were just given by tensor product by some vector bundles. So how do I want to think of this action? So let me observe the following thing. Let's look at the space of connections, G dual bundles with connection on P1. Well, connections on P1 are flat. These are flat connections on P1. They're not terribly interesting. P1 is simply connected. So we only have a single G dual bundle with flat connection, namely the trivial bundle. So we just have the trivial bundle. But the trivial bundle has a lot of automorphisms. So this trivial bundle has an action of automorphisms, which is just constant map to G check. We have a single object, but we have a whole bunch of automorphisms given by its symmetries of the trivial bundle. So these are constant maps from the Riemann sphere to G check. So what does it mean So in a stacky notation, this is what people call the, well, many notations, this is what people call the classifying space of G check. It's something contractible with an action of the group G dual. Okay, so now how do we think of this? So what this tells me is that if I look at a space like this, if I look at O modules, if I look at coherent sheaves on this space, connections G check P1, well, what is an O module in here? Well, it's a sheaf on a point. In other words, a vector space, but with the symmetries of G check. If you really want to have it a sheaf on this object, it's a sheaf on a point with an action of G check. In other words, a representation of G check. If you'd like, vector bundles on the classifying space of a group are exactly a representation of the group, are representations of G check. So the way I want to formulate this, again, is that we have, so that the Hecke operators, so on this side, which are just these tensor product operators, are given by Z G check infinity of P1. So our category of representations of the dual group appears, again, by looking at this category of coherent sheaves on the modular space of connections on P1. So in this formulation, what does the geometric Langlands conjecture say? Geometric Langlands conjecture says so I'm just repeating what I said yesterday, but in funny notation. So the geometric Langlands conjecture says that Z G0 of x is equivalent to Z G check infinity of x for every Riemann surface x, compatibly with the action for every x and x on here of Z G0 of P1, which is identified by the same theorem, by Z, well, identified by the Satake theorem with Z G check infinity of P1. So from this point of view, the geometric Satake theorem, which describes the Hecke operators, can be identified, can be thought of as identifying the theory for on P1. It's solving the geometric Langlands conjecture, if you'd like, on P1. Okay. All right. So this is how I'd like to think of the geometric Langlands conjecture. Okay. Are there questions so far? Okay. So now what I'd like to do today is explain how exactly this picture follows, can be seen from the point of view of topological field theory. So Kapustin and Witten, they derived a form of this conjecture from a fundamental conjecture in physics, from one of the central conjectures in gauge theory, which is the electric-magnetic duality. Electric-magnetic duality, also known as the Montonen-Olive duality, Montonen-Olive S duality, which is a duality of four-dimensional supersymmetric gauge theories. So just structurally, they have two gauge theories. So we get four-dimensional topological field theories, and this is my goal to explain what these words mean. But there are two four-dimensional topological field theories associated to a group G and a parameter, and the S duality for these theories becomes the statement that the theory, which I'm going to now denote by this letter, ZG psi, is equivalent to Z G check and -1 over psi. So these Z's are now denoting four-dimensional topological field theories. And the S-duality conjecture, which I'll try to indicate, I'm certainly not expert on this by any means. So, but what the structure of this is that there's a topological field theory associated to a group and a parameter, and there's an isomorphism of topological field theories that inverts the parameter. And the geometric Langlands conjecture comes from as a specialization of this conjecture. Okay, so this is the kind of format of what I'd like to do today. So I'd like to see why a four-dimensional topological field theory is something like a gadget that assigns to a Riemann surface an object like a DG category, and why what you assign to the Riemann sphere might act on this, and why that's all part of the structure of topological field theory. Okay, so now let me try to explain what is a topological field theory somewhat schematically. So I'm going to try to explain the axioms for topological field theory in tiers. So the first level, I don't know if this is called 1 tier or 0 tier. So let's say this is 1 tier. So what is an n-dimensional topological field theory? Z, everything is going to be over the complex numbers, is an assignment which takes, you start with an n-dimensional smooth, compact, oriented manifold. You go from smooth, compact, oriented manifold to each such smooth, compact, oriented manifold. I'm going to assign a complex vector space, Z of Mn. This is a number. So that's the first tier. So it's a function that assigns to smooth, compact, oriented manifolds, assigns to them numbers. And this has a lot of properties. So one thing that this should be an invariant, should be functorial. Well, in other words, it should just be an invariant of oriented diffeomorphisms. So we're going to assign a topological invariant to manifolds of dimension n, and it's going to have the property that it's multiplicative. And so the multiplicativity is going to say, first of all, if you'd like, the empty manifold goes to 1, and this joint union of manifolds goes to product of complex numbers. Okay, so this is the rough picture of what a topological field theory is.
Is the manifold M allowed to have a non-empty boundary?
Not yet.
Okay.
This is the one tier picture. So far this is something not very exciting so far. So it's a multiplicative number assigned to closed manifolds. And I'm not going to really try to explain the connections with physics, except to say that the idea that this number is supposed to capture some of the properties of path integrals in physics. So we should think of this as something that we write schematically in the following form. We look at an integral which lives over some space of fields on M. Will be a little more concrete later, but there's some space of things we call fields on M, which could be things like functions or sections of bundles or maps to some other target. So there's some typically infinite dimensional space. And we have a functional which is written in the form e to the integral of minus an action of the field. So there's some functional on the space, which think of some kind of Gaussian. And we integrate this thing against some measure on phi. So this is sort of the caricature of where topological field theory comes from. You should think of this as some kind of invariant calculated in this way. So now this is sort of so far not very much structure. the next thing we could try to say is if we really had an expression like this, if a field theory coming from physics, and these are very, very special field theories that are somehow supposed to not depend on a metric on M, so only field the topology of M. But if we have such a theory, we can see what happens when we cut and paste manifolds. So if we take our manifold M and we cut it into two pieces, we have these kind of expressions have some kind of locality. So this number assigned to a manifold should be expressible in terms of numbers assigned to two pieces of which manifold is glued together. So to say this slightly more precisely, we now increase our definition of a topological field theory to have two tiers. So what's the next statement? So we have, I'm going to continue, an n-dimensional topological field theory now with two tiers has the following structure. It assigns to, now I'm going to start with an n-1 manifold. I'm going to keep that structure around, but I'm going to have some more structure. So I'm going to start with n-1 manifold, and my manifolds are going to be compact, smooth-oriented manifolds. Again, without boundary. This is a compact, smooth-oriented n-1 manifold. I'm going to assign to it, and now instead of assigning to it a number, I'm going to assign to it z of n-1, which is now a complex vector space. So this is my assignment. This should have the property, again, this should be functorial. Should be functorial under diffeomorphisms of n. And it should be multiplicative. And multiplicativity here means that, again, to the empty set, I'm going to assign the unit in vector spaces. So vector spaces have tensor product, and the unit for that is the complex vector space C. And it's, I should also, again, disjoint union should go to product, which now is my tensor product. And I should also say something about changing the orientation going to dual vector space. So as you might guess, I'm not actually going to give you a precise set of axioms for topological field theory. But this is part of these are the ingredients. So this is part of the structure, but we also want this structure to talk to what we had before. So we want to say, so what are we trying to capture? We're trying to capture the following picture, that if I give you an n manifold and I cut it along an n-1 manifold, I should be able to figure out the number associated to M in terms of data associated to the two hemispheres and the gluing associated to this vector space. We have a vector space associated to this circle, and we'd like to have some local data on these two patches that we can glue together to get the invariant of M. And so how do we formalize this? So now we say that if you have Mn is now a manifold with boundary, so now it's an n-dimensional manifold, but now I'm going to allow boundaries, then I'm going to assign to it z of Mn, so which is now going to be, instead of a number, we now have a manifold with boundary. So here, I probably shouldn't call it M. Well, sorry. What's another letter? Okay, M del, I don't know. So I have a manifold with boundary. So this is one of these halves. We're going to assign to it now a vector in the vector space associated to the boundary. So this is z of delta M. So to this z of, this is now an n-1 manifold. I don't know, I guess the n-1 goes like that. It's an n-1 manifold. To it, we have assigned a vector space. And the idea is that if you look at this, this hemisphere, this half, it's supposed to have, its invariant will not be an absolute thing. It'll be something that lives in this vector space associated to the boundary. Okay, and then we have to write a bunch of properties of these assignments. And so let me indicate some of the key properties of this assignment. How are these assignments supposed to talk to each other? So, well, for example, what we're going to want is that if you look at a cylinder, so we take an n-1 manifold and cross it with an interval. So this is our picture. So this has two boundary components, one of which is n and one of which is n with the opposite orientation. So we're going to assign to this the identity. This is our topological invariance. The identity, which is an element in Hom of z of n, which is z of delta n cross I by my multiplicativity axioms. So that's one kind of thing. I would like to have that when nothing, I'm going to think of this interval as time evolution, and when nothing interesting is happening, if I just propagate my manifold around in time, that nothing happens. So this is saying that the Hamiltonian is 0. And most importantly, I'd like to say that this assignment should be functorial. So under cobordisms. And what does this say? So we have now, we're going to look at the following kinds of picture. Suppose I give you an n manifold with boundary. Which one do I want? Let's say something like this. Here's an n-dimensional manifold with boundary. So in this case, it's going to get, I'm thinking this manifold with boundary is going to give me a map from the vector space associated to one end to the vector space associated to another end. So this is an element in Hom from z of the circle to, this is supposed to be a circle, not a 0, z of the circle. But now, suppose I cut this, and I think of this as a composition of cobordisms. I want this to be, this element to correspond to composing the map from the circle to circle times circle with the map from circle times circle to circle given by the two pieces. So in other words, if you'd like, we have a map from Hom from z of the circle to z of two circles. And we have Hom from z of two circles to z of the circle, and there's a pairing contracting this. So this is just a slightly clumsy way of trying to say a composition. That you can take this map, and you compose them, and you'll get the map given by the glued manifold. Okay. So that's what we mean by a topological field theory with two tiers. Okay, so now we have enough structure that we can try to actually now we can actually see something. So let me just introduce a little piece of notation. So this is not structure, but just a little bit of notation. That if I give you, suppose I give you such a picture. Here's my M with boundary. Its boundary is called N. And suppose I give you a V inside of an element in the vector space of the boundary, then I want to assign, I can think of this as a label. I'm going to think of labeling this boundary, N, by the vector V. And the way I want to think of this is taking this picture. This picture is now an N manifold with boundary, but now I want to think of kind of closing off this boundary, but by sticking on this label. So I want to think of this as giving me a picture like this, where I've taken the boundary and put a label on it. I want to think of it as something like a closed manifold. In other words, I want to think this picture, for me, is going to symbolize the number, which is take z of m and apply it to v. So that's an element of z of the empty set, in other words, a complex number. Z of m is a map from z of n to z of the empty set, which is a complex number, and I'll just apply it to this vector. So this is just a notation to say that if I have a label, instead of having a manifold with boundary, which gives me a vector space, I'll just get a number. Okay. Okay. So now that's sort of my some notation. And now the first result in this says that if we try to look at topological field theories, we can completely describe them. These two tiers topological field theories, we can completely describe them in 2 dimensions. A 2-dimensional topological field theory is the same thing as a commutative Frobenius algebra. So what is a commutative Frobenius algebra? This means it's going to be a unital commutative associative algebra with a non-degenerate trace. So let me draw what this theorem. So this theorem is very easy to draw. So how do we think of this? So what's the assignment? So given a two-dimensional topological field theory, so let me give one arrow of one direction of this. Given a two-dimensional topological field theory, I'm going to assign to it a vector space, first of all. Let me call it H, which is the vector space associated to the circle. So we're in 2 dimensions. That means we assign vector space to 1 manifolds. There are not so many interesting compact-oriented 1 manifolds out there. So all I need to tell you is what Z of the circle is. Z of a disjoint union of circles is given by tensor powers of H. Okay, so this tells me what Z assigns to 1 manifolds. So now what else do I have? So now I draw a bunch of pictures. So let's take this picture. This is a disk. This is an incoming disk with boundary, the circle. So Z of this picture, what does this picture do? It's a map from what you started to what you ended. So it's a map from Z of the empty set to Z of the circle. Z of the empty set is just the complex numbers. So we have a map from the complex numbers to H. So that's just an element of H. And we're going to call it 1. So that's going to be our unit. So we get a canonical vector in this vector space coming from this picture. Sorry? Z of the empty set as an n manifold is 1. Z of the empty n minus 1 manifold is C, is the trivial vector space. So, okay, that's one piece of picture. We can also draw the picture the other way, and that's one of the key features of these topological field theories. We can draw the same picture going the other way, with different orientations. So Z of this is now a map from H to C. So we're going to call this trace. So that's trace. It's a map from H to C. Now, what else do we have? We have our favorite picture. Maybe deserves a new board. And the favorite picture is the pair of pants. So what does the pair of pants give us? Well, we have 2 incoming circles and 1 outgoing circle. So Z of this is a map from 2 copies of H to 1 copy of H. So it's a product. So this is a map from H, tensor H, to H, which we'll call the product. And now what we can do is, so these are our basic building blocks. We can also do things like we can check, for example, that that if you look at Z of elbow, well, you can write the elbow as a pair of pants which you've cupped off on this side. So Z of the elbow, it's going to be trace of the product. And this is now defining, this is the induced inner product on H. And we can look from the axioms and find out that this is actually non-degenerate. So it's a non-degenerate inner product. In other words, we have the makings of a Frobenius algebra. But what we need to check is that this thing is commutative and associative. So let me just draw, we draw a couple of pictures. Associativity comes from looking at a picture like this and comparing it to a picture like this. So you first compose these two and then add this, or you first compose these two and then compose with this. So these are just funny ways to draw the same manifold. Maybe a little more interestingly is commutativity. And for commutativity, I want to draw the pair of pants in a slightly different way. I want to say I'm going to take this pair of pants and kind of flatten it. And so I can draw the pair of pants as a disk with 2 holes punched out. Okay, so think of these as 2 incoming holes and then 1 outgoing boundary. And then I notice that I can just move these guys around each other. So that's going to give me my commutativity. Just move these two guys around, and we're going to be able to compare the product one way with the product the other way. So we see that this picture is inherently commutative and associative. Okay, so this gives you the ingredients and of the theorem. This gives you the map from topological field theories to Frobenius algebras. And to prove the theorem, you just need to somehow carefully study what happens if I give you some general Riemann surface, general topological surface, and the claim is that I can figure out what to assign to any topological surface by cutting it up into pieces that I already understand. I can cut it up into pieces that involve things like pairs of pants that involve just the ingredients I have before. So I can define a map for any topological surface, and I have to check that this is independent of the way I cut it up. Okay, so that's sort of the indication of this theorem. So now, but I just want to focus on one particular aspect of this, which is this commutativity. And so this gives us a complete description of two-dimensional topological field theories with two tiers. But let's see what's slightly more generally, a more general picture we get out of this, that if I have, if Z is an n-dimensional topological field theory, I'm going to think of what does Z assign to that n-1 sphere. Well, Z assigns to the n-1 sphere a vector space. But the claim is that this vector space carries a canonical multiplication, where in fact it carries, if you'd like, many multiplications that are parameterized by versions of the pair of pants, which we'll call by little disks. So what do I mean by this? So in the case where n was 2, we had this picture. If I give you a couple of small disks and a big disk, I get this is my flattened out version of the pair of pants. And this gives me a commutative multiplication. I can try to draw some kind of picture for n equals 1. So I get a bunch of, so my n-1 sphere is now a pair of points. And now I get a picture given by a bunch of small intervals. So this is my picture that's defining just an associative product on the pair of points. I can't move these intervals around each other inside of the interval. And if I looked at n equals 3, well, so an n equals 3 version of the pair of pants would be you take a ball in 3 dimensions and you cut out 2 smaller balls out of it. So now this is a picture that has 2 incoming S2s and 1 outgoing S2. And now this is, again, gives me a multiplication, and I want to say it's somehow very commutative. This doesn't really mean anything at this point, but I somehow feel that I have a lot more room to move around. Here I can move these 2 points around each other. Here I really can sort of move them around much more freely. And okay, so that's going to make a little more sense in a bit. Okay, so this is the basic picture of two-tier topological field theory. So now what else can we do? Let's just we can have a couple of variants. So some variants of this picture. One thing we could do is we can control the behavior in families. We can look at the behavior in families of topological families of manifolds. So I can require that Z of, say, n-1 manifold is given the structure that makes it locally constant under deformations of this manifold. So what does this mean? This means that if I have a family over some base where the fibers are n-1 manifolds, Well, I can look at Z of each fiber. Z of each fiber is a vector space. These manifolds are locally going to be isomorphic. So these vector spaces are isomorphic, but I want to put that as part of my structure, that Z of n, so now this is a vector bundle over this, it's just going to be a local system. This is going to have a flat connection. So I want to require this structure of rigidity when I move the manifold around. Okay. Okay, so that's just to... This is extra structure. Okay, so and since we've been doing that all week, we might as well also do a DG version because it's fun. So instead of Z of n being a vector space, we can do various variants. For example, we can ask Z of n to be a graded vector space. We get a notion of graded topological field theory. Or we can ask for it to be a differential graded vector space. Vector space, in other words, a complex. So this is just a nice variant of my topological field theory. I'm going to require to every manifold I'm going to assign a complex. I could first just look at a graded vector space, but I'm going to look at a complex. The only thing is now I have more flexibility, because when we have two complexes, we have the usual notion of isomorphism, but we also have a more interesting kind of homotopical notion, which is quasi-isomorphism. So if we have two complexes, when do we really want to say they're the same? When do we want to be able to compare them? We want to compare them when they're quasi-isomorphic. So what does this mean? So I'm going to weaken my axioms. I'm going to say that instead of isomorphisms, I'm going to replace in the axioms of a topological field theory, I'm going to replace isomorphisms with quasi-isomorphisms. So we get a kind of more homotopical variant of a topological field theory. So what does this give you? What kind of structure does this mean? Let me illustrate what does this kind of homotopical topological field theory give you. So suppose I give you two manifolds, n1 and n2. These are n-1 manifolds. So here is my picture. I have lots of different cobordisms between n1 and n2. And in fact, if I look at cobordisms from n1 to n2, this is not just a set, it's a space. There's a structure of a space of cobordism from n1 to n2. So we should somehow, since we're doing something more interesting in homotopical, we should incorporate the structure of this space. So how should we get? So we thought for a single cobordism you wanted to get a map of these chain complexes. What's the kind of homotopical version? If I give you a chain of cobordisms, so I look at the space of cobordisms from n1 to n2, and what I could say is instead of just looking at points, I can look at chains on this space, cochains on this space. And what I want is a cochain on the space to give me a map from Z of n1 to Z of n. So this is kind of part of the structure that I want, is that we have a map from Z of n1 to Z of n2. Z of n1 and Z of n2 are now both complexes. And so we want to, so there's a hom is itself a complex. This is a complex, and we want maps to have this kind of structure that instead of just giving something for individual maps, we get such a chain map from chains on the space of cobordisms to chains mapped between n1 and n2. So this is a way of generalizing the statement that just for a single cobordism, we get a chain map of degree 0.
What do you mean with the chain of?
So this is a topological space, and so I'm going to take my favorite cochain theory on this space, apply it to this. And so say I'm going to take singular cochains on this space. And I want to get, so part of my wouldn't be, so I now have to be more, if I want to put in this homotopical version, I need to be more careful. Instead of saying just for every manifold I give you a map, I want to understand how does this vary? How does it, since map is only a quasi-isomorphism and it lives in some homotopical world, I need to understand how does this vary. So for example, what this tells me, if I give you a point in this space, I'm going to give you a map. But if I have a homotopy, if I have a path, and I change that point, then I'll get a chain homotopy between those two maps. So I'm going to incorporate the topological structure of the space of cobordisms into the data of topological field theory. Okay, so this is, we can take this as sort of a, I don't know, I guess I've said this too much, probably. Take this as a black box, but in any case, what's one reason to make this assumption is that, let me just point out that in this case, you really start in this world, you can really tell the difference between all of these pictures. So in the world of vector spaces, a multiplication on a vector space has two options. It could be associative or it could be commutative. But if I look at a chain complex, I can really tell the difference between having a multiplication that just has an associativity and a multiplication that has a commutativity of this form and a multiplication that has more room to move around. This is more and more, this is a more and more commutative version. These algebras, in the DG world, these things get the name E1 algebra, E2 algebra, E3 algebra, and I can keep going. For every dimension, I have the bigger my dimension, the more rooms the spheres have to move around each other, and the more commutative the algebra. And you can really feel this on this level of chain complexes. Okay, so this is also what's known as A infinity. So it's just associative, but now we're living in some homotopical world. But now we have various versions of commutativity, which are somehow better and better. Okay. So great. So now what do we do next? Well, so that's various games we can play with these topological field theories. What I'd like to do next is move up to 3 tiers. So we're building more and more structure, and we know where we're going with this, right? Because we're trying to see geometric Langlands. So we kind of know that we need a lot of structure around. Let's see this. What's the next level of structure? Well, we can now try to express the locality. Before we had the locality of the invariance of an n manifold under cut and paste. Now we can try to do the locality of z of n minus 1 under cut and paste. We take an n minus 1 manifold, and we might try to cut it into pieces. And we want to try to recover the invariant associated to this manifold from local data. So we're going to take, how do we want to draw this? So here's this is my n minus 1. I might try to write it as a union of 2 intervals over this boundary. So we need to have some kind of gluing law that'll tell us how to get a vector space from, first of all, we need to assign something to the point. And then we need to say how, if I have an interval, I get some kind of data on the point, which will enable me to recover a vector space. So in other words, what we want to do is we want to have some world where a vector space can come as a kind of pairing, or as a kind of inner product. Just like before, we got a number by a kind of pairing. So where is a world where vector spaces can come as pairings between 2 things? That's the world of linear categories. If I have a linear category, that's something where the Homs are vector spaces. So this is one way to say I want to assign to an n minus 2 manifold. So in this picture, I'm just going to have a point. In fact, I won't, in case you're worried, I'm not going to go any further than this. So if you have a point, I want to assign to this n minus 2 manifold, I'm going to assign to it a category. And well, I want a category, and I want my Homs. So this is a category where the Homs in this category between 2 things should be the kind of things I assign to an n minus 1 manifold. So I'm going to get my n minus 1 manifolds invariants as pairings in this form. So this should be a C vector space, or if I want the fancier version, it should be a differential graded vector space. So this category should be either C linear, or if I want to get the fanciest version, I can put this DG version. All I want is I want my homes to be the kind of things I had before. Okay, so now we start getting a whole mess of axioms, because what we need to do is understand how all these different tiers interact. So the first structure that we want is that if you have n minus 1 manifold with boundary, then I want to assign to it now as an object in the category Z of its boundary, which is now an n minus 2 manifold. So this is my version of having a vector in the states of the boundary, in the vector space of the boundary before. I want to have an object in this category. And again, I need to again say that these assignments are going to be functorial and multiplicative, just like we had before. So I'm not going to write down what this means, but these assignments are going to be going to have to satisfy functoriality and multiplicativity. And I want the picture of composition under cobordisms. So let me just draw it this way. If I have, if this is my first manifold, and this is a second manifold and prime, then I want the, so what am I going to get here? So maybe I should just say first that what do you get to such a picture? Z of such a picture will now be a functor from Z of the point to Z of the point. So this, in fact, comes from the kind of arguments that we've been using all week, that functors between two categories are given by something assigned to the square. So if you look at the boundary, so this Z of this thing should be an object of Z of the boundary with appropriate orientations. And now what we've been saying all week is that Z of a product, objects on the product, are exactly the things that give you functors from one side to the other. So in other words, we think of Z of such a thing as being a correspondence that goes from object here to an object here, by kind of push-pull picture. And we're going to require that this composition of functors, that the functor given by this picture is given by the composition of those two. And if you want to keep going, you're going to need to decide what to do with n manifolds. And that's where these kind of pictures come in. If I give you an n minus 1 manifold with boundary, and I give you an n minus 1 manifold with boundary, I can find an n manifold with corners, interpolating between them. And such a picture should give me, so Z of such a picture should be a natural transformation from Z of this picture to Z of this picture. Okay, so this becomes a little cumbersome to write down all of these axioms, but hopefully this gives some kind of feeling of what level of structure we're talking about. Okay, so what happens with our picture here about spheres? So now we can, so let's see what happens to the sphere. So what is Z of an n minus 2 sphere? Okay, so let's see. We're going to draw the same pictures, but we're going to assume that we're now in an n-dimensional topological field theory, and we're assigning to it, we're seeing what it assigns to an n minus 2 sphere. So first of all, it's a category. But we draw the exact same pictures as before. This tells us that the category has a product. Just like before we had a vector space with a product, now we get a category with the product. So it's a category with a monoidal structure. So that's the product on the category. And this monoidal structure gets more and more commutative as n goes up. So if we're looking at the zero sphere, we're just going to get something. So the first kind of thing we can get is just purely just a monoidal or associative. what other kind of things? Another thing that can happen for product on a category, it could be symmetric. Product on a category could be commutative or symmetric. But there's an interesting intermediate world. So in the world of categories, we already see 3 different kinds of products. Unlike in the world of vector spaces, where we just had associative and commutative, categories have monoidal, associative, symmetric, and there's something in between, which is braided. So if we're looking at what a topological field theory assigns, so now a 3-dimensional theory assigns to the circle, it assigns a category with a product, but on the level of categories, you can really feel the fact that going around twice is not the identity. There's nothing here that forces going around twice to be the identity, while in this world, you have so much room to move around that there's no pi1 moving these 2 things around. So categories really feel the differences one level more. So there are only really 3 kinds of categories. There's associative, braided, and symmetric. But again, if you put in the DG, you can feel all the different levels. Okay. Does this picture make some sense?
Well, are all 3 of them associative?
Are all 3 of them associative? Yes. Right. So just like with a vector space, we had associative and commutative, and then you can say more and more and more commutative, but it means the same thing. And with category, you can say it's associative and braided, or associative and symmetric. And those are now 3 different kinds, but if you went further, you wouldn't feel the difference. Unless you're in some kind of homotopical world, where you really feel all these different motions. Okay. All right. But the general picture is the same. And now let me just point out one other picture we can have. So we said that the things you assign to spheres, let's forget about dimensions or categoricity or whatever, what we assign to spheres are algebras. They have this multiplication. Now, what do these algebras act on? Well, so I claim that what I assign to a sphere, it acts on what I assign to anything else of the same dimension. Why? Draw your favorite n-1 manifolds, eh? Here's my favorite n-1 manifold. And first I'm going to do nothing. So doing nothing means you let time go by, and nothing interesting happens. So you just cross with an interval. So this picture represents the identity. Nothing has happened. But now, at some particular point of time, I change my mind, and I say, let me pick a point x in my n-1 manifold. And at a particular instant of time, I'm going to cut out a little ball around this point at this instant of time. So now what does this picture tell me? This picture is a map from Z of what do I have incoming? I have an n-1 coming in, and I also have a whatever sphere this is. And I get out of it n-1. So whenever I tell you, I mean, I kind of want to be careful. I should tell you where I do it, and probably when I do it. But I get an action of this. So if this is a vector space, if this is a vector space, this is an algebra. I have an action of this algebra on this vector space. The same thing is if categories. If this is where a category, and this is a monoidal category, it's a category with a product, we'll get an action of this category on this category, just by drawing these pictures. So that's part of the data of the topological field theory, is that the spheres give algebras and they act on everything in sight. They're the natural symmetries of everything in sight. Okay, so in the second hour, we'll try to relate this picture to geometric Langlands.